Question number 12. Consider differential equation like this, where x domain is restricted from 0 to pi over 2, and then there is the x coordinate and y coordinate is already given. A. Use the Euler's method with step lengths of pi over 12 to find an approximate value of y when x equals 5 pi over 12. Give your answer correct to the three significant figures. So notice that the Euler's method, applying the Euler's method, starting point is pi over 4, adding of pi over 12 one time. So pi over 4 adding of pi over 12 one time will give us 3 pi plus pi over 12, which is equal 4 pi over 12. So notice that if you apply the Euler's method only twice, you will get to the x over d of this point, right? So let's apply it. Euler's method. Euler's method, starting with x comma y. So initial point is pi over 4. Initial y value is pi over 4. And with the step size, delta x equals pi over 12. Applying delta x for the first time, we will get 4 pi over 12. We don't know the y value. Initial Euler's method, one more time, we will get the x value will be 5 pi over 12. You don't know the y value yet. So all you need to do is find this y value over here. Okay, Euler's method is defined like this. X to the next value, x to the n plus 1, is always xn plus step size, which is pi over 12. And y yn plus 1 is defined as yn, previous y value, plus step size, pi over 12 times dy over dx. So dy over dx is we can find over here by moving this term to the right side. And then notice that the cosecant of 2x is 1 over sine 2x. So we can write over here dy dx as, okay, yn divided by sine of x, sine of 2xn, right? Plus square root of tangent xn. So we can apply this method. Okay, let's use calculator to find out how it looks like. So first value here, let's define, to make it simple, pi over 4, let's define this as large x value. This one is also large y value, and pi over 12, we can define this as value, right? So I'm going to do pi divided by 4. I'm going to store it x, and then y is also the same. This stored as also y value, and then step size is what is it? Pi divided by 12. I'm going to define it as store it as step size as value. See, and then yn plus 1, which is this value over here, is defined over here. So starting with yn plus 1 equal yn, which is y value, plus step size, pi over 12 is s value, times that is y value divided by sine of 2x value, right? Plus square root of tangent of x value. Because we already stored x and y, we can calculate this value is 1.252. So this value here, here is 1.2528. So storing this value again to the y value, let's define this is new y value, and then x value is now 4 pi divided by 12 is now becomes new x value, right? And then this x and y, put it together over here, So because I already trained s and x and y value, s step size remain the same. This will give us answer for the next step. So here, so it's gonna be, so answer will be 1.98 by 3 significant figure. Yeah. So so an x is 5 pi over 12. Y will be, y is estimated how much? 1.98. 1.98, which is by Euler's method. Okay, so the answer is this one. Show that differentiating this one is that one. Okay, differentiating that one, this we have to apply the chain rule, right? So ln of fx, so differentiating that function, 1 over 2 goes in front, ln of fx is 1 over fx. So 1 over cotangent of x times f prime of x. So differentiating cotangent of x, I need to see the formula booklet. Differentiating cotangent of x will give us negative cosecant x squares. So negative cosecant square of x. So this is going to be 1 over 2. Cotangent of x is tangent x, which is cosine x. Down on the top is going to be sine x over cosine x. Negative cosecant x is 1 over sine square of x. Okay, sine x, 1 over sine x is cancels out. And then bottom part is only remaining 2 sine x cosine x, which is 2 sine 2x, negative 1. So it's going to be negative 1 over sine of 2x. Which is equal to 1 over sine 2x is equal to the cosecant 2x, so negative cosecant of 2x. So this one, that one, same. Okay. Show that the square root of cotangent x is integrating factor for this differential equation. So this differential equation is here. So this is the basic format of integrating by factor method. Dy dx is here, y is here, so px will be a negative cosecant 2x, and qx is right there. So so integrating factor of that equation is, so ix is e to the integral of negative cosecant of 2x dx, which is equal, we already showed that differentiating this one will give us that one, which means that we can integrate that one will give us this one. So negative, so e to the, so it's going to be e to the 1 over 2 ln cotangent x, ln of cotangent of 2x or x, cotangent of x, yeah, cotangent of x, yeah. So this can be rewritten to e to the, so I just get rid of, not get rid, this number, 1 over 2 can go up there, no problem, right? And then this e ln cancels out, and then this one becomes square root of cotangent of x. So this one. Hence, by solving the differential equation, show that y equals this one. So multiplying of what? The square root of multiplying square root of cotangent of x on both sides, and then doing the integral. This equation will give us y times square root of cotangent of x equal right side integral square root of tangent of x times square root of cotangent of x dx. And this expression here, see, this is 1, right? This is 1. Tangent x times cotangent x is 1. So we can say y square root of cotangent x equals integrating 1 dx is equal x plus c, and then putting this coordinate into here, we get the c. So directly putting that coordinate there, so it's going to be y is pi over 4. Pi over 4 square root of cotangent of pi over 4 is 1 over here, and then x plus c. X is pi over 4 plus c, which is c equals 0. So c becomes 0. So this, we can just get rid of this one. So therefore the particular solution y equals x divided by square root of cotangent of x equal so it's x divided by square root of 1 over tangent of x equal x square root of tangent of x. So this solved. Okay. Consider the curve y equal x square root of tangent x from x from 0 to pi over 2, and Euler's method approximation calculated from part A. Find the y coordinate of this one when x is 5 pi over 12. Give you a correct answer. So what you need to do is we need to find the y coordinate of that one. So when x is let's say x is pi over 4, so pi over 4 times square root of tangent of pi over 4, that's 1, right? So this value, no? Is 0.785. Is there that much of error? Oh, when x equals 5 pi over 12, right? So, okay, so let's say 5 pi divided by 12. Let's store this is x value, and then we'll put the x times square root of tangent of x. So it's going to be 2.53. So it's going to be 2.53 by 3 figure. By considering the gradient of the curve, suggests the reason why Euler's method does not give good approximation for the y coordinate. So we can answer the gradient must be increasing rapidly at x equals 5 pi over 12. So the Euler's method underestimates. State why this approximation is less than y coordinates at x equals 5 pi over 12. Yeah, this is basically the same answer. Because y equal x square root of tangent x is concave up near x equals 5 pi over 12. So you can easily estimate, see the y over x, there's no domain problem, but tangent of x, when x approaches pi over 2, this is vertical asymptote of tangent of x. So notice that 5 pi over 12 is very near to pi over 2, which is 6 pi over 12. This is pi over 2. So when any x value approaching pi over 2, the tangent function goes rapidly up. By considering dy dx, this one deduce that the curve y tangent of x, y equals x squared tangent of x, has a positive gradient. Positive gradient when x is like this. See this function. This function can be rewritten, the dy over dx. Dy over dx can be rewritten y cosecant of 2x plus square root of tangent of x. And x domain restricted from 0 to pi over 2. So x is positive value. When x is positive value and y value is already positive, so notice that this is y over sine of 2x plus square root of tangent of x. And then notice that the tangent value between 0 to 2 pi is always positive value. Sine 2x between 0 to 2 pi is always positive value. Y value is already at the positive value. So notice that this whole dy dx is always greater than 0 when x equals 0 to pi over 2. So that is the answer. So